Welcome to Lecture 20, the final lecture for ME 436 this year. Today I'm going to briefly talk about turbochargers, how they're implemented, and then a brief recap of what we've covered in this course. So let's talk about turbocharging in a diesel engine. Most often turbos are applied to diesel engines. They are now in spark ignition engines as well, but originally they were developed for very large marine type diesel engines. So the thing to note is that we're throwing away a lot of potential work during that blowdown phase. There's still useful energy in that mass as it leaves the cylinder. And there's also useful work as the piston is pushing the final bit of the exhaust out. So the premise of a turbo is to harness a portion of that exhaust energy, convert it into useful work, and then use that useful work to turbocharge the incoming air. If we look at, this idea of complete expansion. So in an Atkins cycle, you would have a complete expansion down to state 7, and you'd get this additional work. A turbo is trying to capture that work and then use it to replace this pumping work with supercharger work. So if I took some of this work and use that to supercharge the inlet, now the cycle is going to increase and there's going to be more available work. So that's what I'm trying to show in this additional, this second graph on the right, is after you supercharge it, there's now even more potential work in the exhaust. Now this is a virtuous cycle, but it doesn't continue indefinitely. At some point, the inefficiencies in the turbo and the compressor balances these two out, because the area here is related to the work available in the fluid, and the area here multiplied by the turbine efficiency multiplied by the mechanical efficiency of that turbo and then multiplied by the compressor efficiency should equal this area here, which is the work we are able to do on the incoming air. So at some point, as you increase this supercharging, you're going to farther increase this available work in the exhaust, but because of those inefficiencies, things will balance out. Now, it's impossible to recover 100% of the potential exhaust energy. You would need the pressure between the cylinder and the turbine to rise instantly. So you'd basically have to have that turbine fan directly next to the engine with no volume between them that takes time to pressurize. And then you need a perfect isentropic expander that was perfectly isentropic at a huge range of flow rates and pressure ratios, something we cannot design a rotor to do. So if you were to do this, you would have the pressure would continually spike every time the valve opens, and then it would steadily decline, and then it would be flat after the exhaust stroke, and it would remain flat until the next cylinder opened up. The alternative to that is what's known as constant pressure turbocharging. So this is typically used in those large marine engines that turbocharging was developed for. If you put a very large plenum between the engine and the fan, it will take so long to charge. So each charge of air coming out of a cylinder will only partially increase the pressure of this volume. So it remains close to constant pressure as the engine's running, and thus the turbine fan can spin at constant speed and provide a steady amount of boost to the compressor. The large volume essentially dampens the pressure spike behavior. So the drawback to this for automotive applications is there's an extremely large turbo lag, as well as the fact that this volume takes up a space that's equal to, 1.5 to 6 times the displacement of the engine. So if you had a 4-liter engine, this could be as much as a 25-liter plenum, and that's half the size of your gas tank. So it'd be a very large volume of a pressure vessel that you need to have there. So these don't make sense in automotive applications. So what cars typically use is something known as pulse turbocharging. They're not quite as efficient, but they can be more compact and still capture a significant portion of the high pressure energy from blowdown. The drawback is with valve timing. You really have to have the valve timing correct to avoid scavenging issue. So that's what I'll talk about on the next slide. The volume or the pipe length distance between where the engine exhaust valve opens and where the turbine fan is critical for determining what pressure the exhaust valve will see when the inlet valve opens. So let's look at case 1 here. When the exhaust valve opens, this tube, this volume between the exhaust valve and the turbine, quickly pressurizes because it's coming out of the engine faster than it can move through the turbine because the turbine has to speed up. So then it reaches that pressure and it starts flowing through the turbine faster than it flows through the engine because now there's less mass coming out of the engine. It's not blowdown anymore, it's the piston pushing the mass out, and that flow rate is less than what goes through the turbine. So the pressure starts to drop. And then you get this reflected wave, just like when we were talking about those resonators, and the pressure seen at the exhaust valve when the inlet valve opens is quite low, and hopefully at or below what the incoming fresh air pressure is, because we don't want flow back through that exhaust valve. Now case 4 is an example of a very short exhaust valve tube, and generally works out okay. Similar thing, that the pressure has dropped before the inlet valve opens. Case 3 is okay. There might be a little bit of backflow, but case 2, this particular length of tube causes a significant portion of the exhaust mass to go back into the engine through the exhaust port because the inlet valve is open during that time. So that's generally what we want to avoid. So we need to, since the runners between the different cylinders and the single turbine will be different lengths, we need to ensure that none of the cylinders wind up in arrangement 2 and that they are all either in 1 or 4. So with pulse turbocharging, one of the important things to do is to link up several cylinders to a single turbine, because we don't want to have a turbine for each single cylinder and have that turbine sitting there spinning with no mass flow during the whole power cycle of the engine. So typically 3 cylinders are connected to a single turbine, either 2 or 3. If you try and connect 4 cylinders to the turbine, because of the way one would be in blowdown phase while another one was still open, you would get basically mass blowing from one cylinder back into the other cylinder instead of through the turbine. And we don't want to do that. So that's why we limit ourselves to 2 or 3 cylinders per turbine. So let's look at the top part of this diagram that comes from your textbook, I believe. If we've got atmospheric pressure down here that we're exhausting to, and we've supercharged our inlet, so the inlet manifold pressure is a bit higher than atmospheric. We're going to come around here to this point, and this first bar is where cylinder 1's exhaust valve opens. And as soon as that exhaust valve opens, the pressure between the cylinder and the turbine rises very quickly, and then it spins up the turbine and it flows through the turbine, and then the cylinder starts exhausting less and less, so the pressure starts dropping, and it's going to keep dropping closer to atmospheric because remember it's venting to this atmospheric pressure. And the goal here is this crossover point. We want that crossover point to occur before the inlet valve opens for the next cycle. That way the fresh air will actually help push the last remaining air out of the cylinder and into the exhaust. So then the next cylinder opens here at this bar, or sorry, next cylinder opens here and begins repressurizing that tube between the engine and the turbine, and that process repeats itself again. If we tried to put 4 cylinders on a single turbine, we most likely wouldn't be able to engineer this crossover point to occur before the next inlet valve opens. Now, you may think, I have a V6 engine under my hood and I know there's only one turbo. Well, it's possible to feed 2 inlets to a single turbo. So you may have your fan and there's a rotor, a single rotor, but you're feeding 3 cylinders to one side and 3 cylinders to the other side of this fan, so that there can never be cross flow from this bank of cylinders into the other bank of cylinders. So it is possible with a single mechanical device, a single turbine, to serve 6 cylinders, but when that's the case, it's really just 2 turbines mated back to back. They're not linked flow-wise. The flow of 6 cylinders is not linked in one pathway, if that can make sense. So I have a quick example about a plenum volume type turbocharger, and then we'll be done for the lecture here. So I've got a turbocharged 4-stroke compression ignition engine. It uses a plenum to exhaust to dampen the exhaust pulse, and the temperature and pressure of that plenum is 1200 Kelvin and 200 kilopascal. And we're going to assume that that plenum is driving a turbine with an average efficiency of 45%, and that it's connected to a compressor that's supercharging the inlet that's 58% efficiency, 58% efficient, and the mechanical transfer efficiency is 92%. So that's just the friction on the rotating shaft. So the question is, for this particular engine, what is the boosted inlet pressure? And we're given some standard ambient air conditions. So the solution to this is a formula I presented a couple lectures ago, which derived this equation from, we had a diagram of going through a compressor. So state 1 was before the compressor, and then state 2 is after the compressor, and then we had the engine with its internal states, and the exhaust of the engine was state 3, and then the turbine exhaust was state 4. So with that numbering of things, that's where this equation came from. And so we're curious about what is the boosted pressure here. So P1 is our atmospheric pressure, P2 is the boosted pressure that I want to solve for. P3, after the engine, that's going to be our plenum volume pressure, and P4 is our ambient exhaust pressure. So in this particular problem, I believe I was given everything needed to fill in this equation, and I'm rearranging and solving for P2. So that's what this looks like. P2 is a function of P1 and all of this. We substitute in the numbers given in this problem, and I find that the engine was boosted to 176 kilopascal inlet pressure. So that's it for turbos. I want to briefly recap what we've done in this course. We started with ideal engine analysis. We worked through Otto cycles, diesel cycles, dual cycles even. And what assumptions did we make for those? Well, first off, we typically did the cold air standard analysis. We assumed combustion was instantaneous in the Otto cycle. We assumed sometimes no pumping work. we almost always, in those basic assumptions, assumed that the valve openings were instantaneous and that they occurred at top dead center or bottom dead center, so that we separated out the 4 strokes of the cycle to just be an intake stroke, a compression stroke, a expansion stroke, and an exhaust stroke, with combustion happening instantaneously. We showed so those were the ideal things we did, and then we worked through a whole host of modifications to the real analysis. We worked on corrections for fuel and air rather than treating it just with air, so we worked with the diesel cycle. We worked with pumping losses. We talked about friction losses a little bit. We didn't delve into that too much, but they are generally a function of the speed the engine is operating at. We've lumped all of that into the mechanical efficiency of the engine, but that mechanical efficiency really isn't constant. So a more detailed analysis would treat that as a function of the engine's speed. We spent a while going through the stoichiometry, the fuel-air combustion. We worked on incomplete combustion when we talked about equilibrium. We talked about the things that are occurring in finite time. So we removed a lot of those timing assumptions. So we talked about the timing of when valves open and close. We worked with the time that combustion takes to occur, related that to flame speed in an SI engine. We did a little problem with homogeneous ignition time for a CI engine. We talked about swirl and tumble and how they increase the turbulence so that you have, and the mixing so that you have a faster combustion. We talked about blowdown losses, or just about blowdown in general, and today we talked about how a turbo can take advantage of some of that work potential in the blowdown. We talked briefly about blow-by loss. That's the loss of what works its way past the piston head in the cylinder, and is a general loss factor in the engine. And we've mentioned at times, but haven't delved too deeply into heat loss as the main factor limiting reducing efficiency in the engine. All of these led to some real engine limits that we've discussed. We talked about engine knock and misfire. Engine knock occurring at typically low RPM when you have enough time for that homogeneous ignition to occur. Misfire occurs, generally speaking, at higher RPMs, and you're not getting the right air-to-fuel ratio into each cylinder. We talked about mechanical stresses a little bit. We didn't talk too much about cam lobes this year, but we did talk about trying to have, we don't want necessarily instantaneous combustion because we want that pressure rise to be a smooth function, so we don't want a detonation. We want a nice, smooth, but quick flame front. We did spend a few weeks talking about emissions. What are the types of emissions, what lead to emissions, and how we clean up emissions, and those are real critical design factors in the engine. We've spent the last couple of weeks talking about fluid flow. We spent a lecture on compressible fluids and talked about the choking at the valves and restrictions on the intake and exhaust manifolds. So that's a real part of engine design today, is getting those valves designed correctly to maximize volumetric efficiency and reduce all the losses associated with that. And then I've only briefly touched on this, but another major issue in designing engines today is making sure everything seals up nice and tight, and thermal expansion is what limits how tight we can make that machining tolerances. So with that, I'll conclude, and thank you for listening to these lectures.